Hi there, guys. Happy Valentine's Day to you. Is it sad that this is the most exciting thing I'm doing all day? Yeah, probably. But let's get going. So, last time we had a review session, we covered all of the limit stuff, all the derivative stuff. So, today we are going to be mainly discussing integrals. And I decided not to cover infinite series because it was something that we covered so recently that we don't really need to review it that much. And plus, my YouTube channel has plenty of videos on the infinite series material. Hang on, I'm going to close my window real quick. Sorry. So like I said, we covered infinite series so recently that it doesn't even really make sense to review it at this point. So we're going to be mainly just talking about integrals. So let's get into the theory of what integration really is and review the concepts in the theory a bit before getting into the practicals. So what does an integral do? So we know that integrals are the opposites of derivatives. We know that they're opposites in the same way that addition and subtraction are opposites, multiplication and division, logs and exponents, things like that. They have that same inverse relationship that we see come up many, many times in math. So it doesn't even really make sense intuitively. How can something that gives us the slope of the tangent line to a curve be the opposite to the area under the curve? And I haven't gotten high enough in my own math journey to answer that yet, but let's just take my word for it that they are indeed opposite. And how are they connected? They're connected by something called the fundamental theorem of calculus. But before we even get into that, let's talk about what they do. So we know that derivatives tell us rates of change, which is useful in just about every area of science, economics, engineering, medicine, so on and so forth. Integrals tell us the area under a curve. So let's say we have some generic function. And this isn't a real function. I'm just making something generic looking. So we have an interval going from A all the way up to B. So an integral of this function tells us the area underneath the curve bounded between point A and point B. So it would look something kind of like this. If we use, I'm already using A for area. Here, how about capital A for area and lowercase a, lowercase b for the endpoints? So the area under the curve, A, is equal to the definite integral going from our low endpoint up to our high endpoint of our particular function. In this case, we have f of x dx, and we'll go over what all of this means in just a second. We'll review all of this. But where does this come from exactly? Well, remember that we didn't even really start with integrals. When we're trying to find areas, we did approximations. We did what we felt was the best possible approximation given the circumstances. So we took what we call a Riemann sum. We took some rectangles and we brought them only as high as the curve itself. So when we're deciding how high to make a rectangle, we stop when we reach the lowest possible part of the curve. We have a series of rectangles, just like that. Oh, Nathan is joining us. That's a pleasant surprise. Hey, Nathan, glad to have you with us. So back to what we're doing now. The idea is that we're just going to add more rectangles to get what we feel is maybe a sufficient approximation for the area. So as you can see, it's pretty bad. We have all of this untapped area right here that generates a large margin of error. So how did we respond to that? How do we get a more accurate area? What we did is we made smaller rectangles. So what we could do is maybe we could take these and we can take half of each, half of the interval. So for example, each of these have a width of delta x. How about we cut delta x in half? How about we make them just half as skinny, or half as fat, I guess would be the word. So we have one rectangle right there, one right there, and then we're going to just keep on with what we're doing right now. It doesn't help all that much. So we may even have to get maybe a bit smaller than that to get an acceptable approximation. And things are getting kind of hard to see. I might use a different color for this. So as you can see, the more rectangles we have under the curve, the more accurate our area becomes. The closer and closer we get to the actual area under the curve, the 100% actual area. So it begs the question, how many rectangles do we have to keep adding in order to get the perfect 100% correct area that we know it is. So the answer, we remember it has to be infinity. In theory, we have to add an infinite number of skinny rectangles to get the exact area under the curve. Having a finite number of rectangles isn't going to work. No matter if we have 10 rectangles or 100 or 1,000 or 10,000 or a million, we won't truly have the correct area under the curve until we have theoretically an infinite number of rectangles. So how do we even approach a problem like that? I mean, we know how to add rectangles together. I mean, by this point, we're pretty good with arithmetic, we would hope. So how do we even conceptualize adding together an infinite number of rectangles? So we have to use the limit. And this is why the limit is such an important tool, such an indispensable tool for learning calculus. We remember that limits are used to determine the derivative of a function. We remember that there is the limit definition for the derivative of a function, and now there's also the limit definition for the integral of a function. So we have all the derivative rules, we have all the integral rules that help us take integrals of functions, kind of like what we have for derivatives. With derivatives, we have chain rule, product rule, quotient rule, all that stuff. Integrals, we have integration by parts, we have substitution, we have all the trig rules, but we have something that we can fall back on, a foolproof way we can integrate anything, kind of like what we have for derivatives. So I shouldn't have erased that. I'll bring that back. So this area, this definite integral right here, we want to provide a rigorous definition of how to get this no matter what. We want to find a foolproof, rigorous way of getting the area under the curve between two endpoints. So we want to rigorously define the definite integral as being the limit as n approaches infinity. And I'm going to take this bit by bit and explain every part of this as we go on. So I'm going to just write everything first. So we're going to have the limit as n approaches infinity. Then we're going to have the Riemann sum. I think I can make that look a little nicer. The sum going from I, going from I equals 1 to n of f of c sub I times delta x. So it's really big, it's really scary looking. There's a lot of symbols, there's a lot going on. So let's take it bit by bit and understand what's really going on here in this expression, in this equation. So this limit right here, we're going to start with that, taking the limit as n approaches infinity. But what is n exactly? Well, in this case, n is just the number of rectangles. So when I first drew this really ugly looking graph, we had, I think, 4 rectangles. I'm pretty sure we all agreed that it wasn't a very good representation of the area at all. So we just kept adding more and more and more rectangles. So n is the number of rectangles. The only thing this limit is saying is that we're taking the number of rectangles towards infinity. We're going to keep adding more and more and more skinny rectangles until the number of rectangles is infinity. That's all what that limit means. This sum right here, I equals 1 to n, well, we know that n is reaching infinity, which means that ultimately we're going to be adding together an infinite number of things. We're going to be adding together an infinite number of whatever this is. And then let's talk about what that part really means, f of c sub I. So this kind of trips up a lot of people. It tripped me up when I first took calc. The teacher didn't really explain it all that well. F of c sub I occurs when you pick any generic point on the x-axis. So I'm just going to maybe pick this one, for example. So I'm going to call this c sub I. So if this is c sub I, graphically, what does f of c sub I look like? Well, we know f of x is what we get when we plug in an x value. F of c sub I is what we get when we plug c sub I into whatever function we have. So in this case, this ugly function that I drew is f of x. So we're going to just plug c sub I into our function, and it generates a function height right there. So this point right here has coordinates c sub I comma f of c sub I. That's all that is. F of c sub I is just the height of a rectangle. So what if we didn't want to find the area of all of them? What if we just wanted to create an expression that returned the area of just one single rectangle? So we're going to need base times height. We remember from geometry that that's how we find the area of a rectangle. So I'm going to pick just any generic rectangle. Maybe the one we already have would work pretty well. So let's see if we can create an expression to find the area of just one rectangle. So that's going to be base times height. So we know what the height is. We can clearly see that the height of this rectangle is f of c sub I. But then what about the base? That's where this delta x comes in. Delta x is always going to be the difference between two consecutive x values, no matter what they are. Delta x is going to be uniform, whether we're talking about this rectangle or that one or that one. Delta x is going to be the same for every single interval that we select. So delta x is going to be the base of a rectangle, any rectangle we choose. So that means the area of just one single rectangle is going to be delta x times f of c sub I. And again, I kind of wish my teacher explained what all this means. They just kind of threw it at us and we didn't really know what to do with it, but that's just kind of what it means in basic terminology. We're just taking the area of one rectangle, and then the sigma outside, this Greek letter sigma, means we're adding together, again, this is an infinite number of these rectangles. So we're taking the number of rectangles up towards infinity, and we're going to add together all of these consecutive areas to present the area under the curve. We're going to have the 100% perfect area under the curve only with this limit. If this limit didn't exist, the best we could hope for is an approximation, but the limit is such a powerful tool because it gives us exactly what we're looking for, not just an approximation. So let's get into the theory of integration, how the process actually works. So we know by this point that integrals are based on the concept of an antiderivative. So for example, if we have some function, I always like using x squared as a generic function, it works pretty well. Let's say we have f of x is equal to x squared. So that means if we want to take the derivative of course is f prime of x, we're going to get 2x as the derivative. But what does that mean in terms of integration? So what that means is that if we want to travel backwards, let's say we have f prime of x and we want to find f of x. We're not trying to find the derivative, we're trying to find the function that has this derivative. So what if we have the 2x and this right here is unknown? How do we find a function with this given derivative? So we're going to have to do the inverse of taking the derivative. We're going to have to take the integral. So it's all kind of connected through the idea of the fundamental theorem of calculus. And there are two fundamental theorems of calculus. FTC for short, there's FTC1 and FTC2. Fundamental theorems of calculus. So one of them tells us that derivatives and integrals are opposites. It tells us that, for example, y is equal to dy dx of the definite integral going from 0 to x of f of t times the differential times dt. So I guess I want to keep the notation uniform. I think instead of a y, I'm going to just call that f of x. I like that a little bit better. I'm keeping things uniform as much as I can. So it's one of the two fundamental theorems of calculus that tell us that the derivatives and integrals of functions are opposites of each other. So in this case, we can see that this is going to cancel out with that. And the interesting thing to note is that whenever we do this, we're going to replace our variable of integration with our upper limit of integration. So in this case, it's no longer going to be a function of t. We're going to transform it into a function of x. And that's what happens whenever we integrate something like this and we put our upper limit of integration in for the variable. It turns into f of x instead of f of t. So that's what the first fundamental theorem of calculus tells us. Derivatives and integrals are opposites of each other. And now what about that other part, the second fundamental theorem of calculus? Well, that is the particular thing that tells us that the area under the curve is equal to the definite integral. So the thing we just saw a few minutes ago with that scary looking limit, the Riemann sum equal to the integral, that is what the second fundamental theorem of calculus tells us. So let's maybe use an example real quick. Let's say we have just the function, maybe square root of x would be a good one. I want to pick nice, easy x values to work with. How about 0 and 4? So we're trying to find the area under the curve. And this time we don't want an approximation. We don't want to add together a bunch of rectangles. We want to get the actual area. So we're going to do the integral. We're going to set this up so that we can find the actual area and not just an approximation. So I always use a capital A as shorthand for the area under the curve. So area, this particular area that we're looking for, is going to be equal to the definite integral. And this is just the integral. Remember that whenever we see this, this is just the sign for an integral. An integral can be definite or it could be indefinite. So a definite integral is going to have limits of integration. We're going to have something below, we're going to have something on top that tells us where to start and where to end. Whenever we have a start and an end, that's a definite integral. Whenever we don't have anything like that, it's a definite integral. So the fundamental theorem of calculus tells us that in order to find the area, we have to make it a definite integral. So we're going to go from 0 to 4. And then we're just going to integrate whatever our function happens to be. So in this case, it's going to be square root of x dx. So let's just maybe give ourselves a reminder on why we have to put dx. So originally, we're pretty good with derivatives by now. We know that the syntax of a derivative looks like this. It's just going to be some generic function. So what happens if we have dy dx, but what we really want to find is just y? What if we want to find the function that has this derivative? So the fundamental theorem of calculus part 1 tells us that we have to integrate both sides. And actually, before we do that, it may be helpful just to perform a quick separation of variables. It would look like this. We're going to multiply both sides by the differential dx. And this is what our separation of variables looks like. We have the dx differential along with f prime of x, and we have the dy differential all by itself. So we're going to integrate both sides now that we have it in the form that we want. And the integral of dy is just going to be y. And then if we take the antiderivative of a derivative, we just get the function itself. We just get f of x. So that's why we have to put the dx, because it comes from this differential equation right here. We perform the separation of variables, and we get what we expect the integral to be. We get what we've always known it to be. So that's where that differential comes from. That's why we always have to make sure we put the dx at the end. Because remember with the Riemann sum, with the limit that we talked about a few moments ago, we had the delta x. Now, what is the difference between a delta x and a dx? So a delta x is going to be a discrete, I can't talk today, sorry. It's going to be a discrete unit of distance. So it's something that can be measured. Dx, on the other hand, can't be measured. So delta x can be measured. Dx is going to be infinitely small, as close as it can get to 0 without actually being 0. This is the product of a limit. This right here is the product of ordinary algebra. So that's the difference between delta x and dx. So now that we have that groundwork laid, let's go ahead and see if we can integrate this. So remember that integration is the opposite of differentiation. Integrals and derivatives are opposites of each other. So what we want to do is we want to write this in a form that makes it easy to find the antiderivative. And then we can use some of the integration rules to help us through this one. So maybe instead of square root of x, I want to use the exponential notation for the root. I want to make that x to the 1/2 power. It's the same exact thing, it just looks a little bit different. The reason why we want this instead of the radical is because if we're taking the derivative, we're going to apply the power rule. We're going to multiply this by the exponent and then subtract 1 from the exponent. We're going to do the exact opposite this time because we're going backwards. When we do derivatives, we do one thing. When we do integrals, we do the exact opposite of whatever the differential operator has us do. So we're going to add 1 to this exponent. A 1/2 plus 1 gets us 3/2. So we're going to get x to the 3/2 power. When we're doing derivatives, we multiply by the exponent. But when we're doing integrals, we're actually going to divide. So we're going to divide by our result. We're going to divide by 3/2, which is the same exact thing as multiplying by 2/3. And it's the fundamental theorem of calculus, the second part of that tells us that we have to take whatever the antiderivative is and evaluate it at the two endpoints. So we're always going to start with our top endpoint. We're going to have 2/3 out front is not going to change anything. Having it outside versus having it inside the brackets. We're going to plug in 4 first of all. We're going to get 4 to the 3/2 power. And then we're going to subtract the exact same thing we get when we plug in our low endpoint instead of the high. So we're going to plug in a 0 instead of a 4. Same exponent. We're going to evaluate this and see what we get. So the answer to an indefinite integral problem will always be a function. It'll always end in c. The answer to a definite integral problem is always just going to be a constant. It'll never be a variable or a function. A definite integral problem is always going to result in a number as your answer. So let's see if we can grind through this real quick. So 0 to any power, still going to be a 0. But then what about this right here? So the way I would probably look at this one is I would take the square root first. This is 3 times 1/2. 4 to the 1/2 power is 2. And then 2 to the 3rd power is 8, which means this entire thing has a value of 8. So we have 8 times 2, which is 16 over 3. And that is our answer. That is the area under the curve. All right, they work pretty well, but what happens if we get something maybe a bit complicated? Well, this one isn't that bad, but I feel like we should still talk about it a little bit first. So how do we integrate cosine of x? So another way of thinking about this would be asking ourselves, what function do we take the derivative of to get cosine of x? And that would be sine of x. If we take the derivative of the function sine of x, it tells us that we get cosine of x as our answer. So if we want to apply the first part of the fundamental theorem of calculus and work backwards, we're going to get that the integral of cosine of x gets a sine of x. When the derivative and the integral cancel each other out on the left side of the equation, we're left with sine of x. So this is going to be sine of x. But I forgot something. I forgot a plus c. Let's talk about why we have to have the constant there real quick. So what if we didn't have just cosine of x? What if we had something a little bit different? Whoops. Erased a bit too much there. What if we had maybe sine of x plus 2? So we know that the derivative of sine of x is cosine of x, but then what is the derivative of 2? Derivative of any number is going to be 0, so the derivative is not changed by having the 2 there. Having the 2 does not change our derivative whatsoever. But if we want to work backwards, this presents us with a bit of a problem. How do we account for this being there when we took the derivative and having nothing there when we take the antiderivative? So we lose information when we go from the derivative to the integral. So that's why we always have to have the plus c there, to account for the fact that there could have possibly been something there before, even if we can't see it now. And there is a way in certain circumstances you can find c. We call that an IVP. We call that an initial value problem. We could maybe have something like this. I don't know, I want to come up with a generic one. Let's say we have maybe 2x dx. And then let's say we have f of 0 is equal to 1. So with something like this, with an initial value problem, it's possible to solve for the constant of integration. Works just like this. So we're going to take the antiderivative the same way we always do. We're going to maybe move the 2 out front, make things a little easier to conceptualize. And then now we're just faced with the antiderivative of x. We're being asked, what function do we take the derivative of to get x for our answer? We can apply the power rule for integration here. We're going to add 1 to the exponent. It's going to turn into a 2. Then we're going to divide by that result. We're going to divide by 2. So we're going to have 2 times x to the second power, and then we're going to divide by the result, divide by 2. And then we have plus c. This is a definite integral. We do not have any endpoints on there. This is going to just be a definite integral of function ending with c. So we have 2 canceling with 2. We just have x squared plus c. And I'm just going to call that f of x. All right, but then how do we find c? So what we can do is we can plug in 0 for x. So instead of f of x, what if we wanted to find f of 0? So I'm going to take everywhere I see an x, I'm going to replace them all with 0. So this x turns into a 0. This x also turns into a 0. And they tell us that f of 0 is equal to 1. So now we have 0 plus c is equal to 1. So then that's how we know that the constant c is equal to 1. So that's how an initial value problem works. That's how we can use a little bit of algebraic logic intuition to help us solve for the constant when we're given an initial condition like this one. So let's talk about maybe a bit more of a complicated case of an integral. What if we had something like this? What if we had cosine of pi times x dx, and let's make it a definite integral. Let's say we're going from pi over 3 to 5 pi over 6. So what do we do there? So this is how we know we have to do a substitution. Remember, a substitution occurs whenever we have something that's a clear outer function and then a clear inner function. It works really, really well if we just happen to have the derivative of the inner function present in the integral. And let's figure out what that would look like real quick. So we're just kind of hardwired by the time we get to this point in the class, kind of just hardwired to make u whatever happens to be the inner function in this integral. We can see that the pi x is going to be the inner function. So it is a really, really good candidate for u. And then we, of course, want to take the derivative, as we're used to doing by now. Derivative of u with respect to x is just pi. And then we want to do another separation of variables, multiply both sides by dx, so we get the following. We're just making a quick modification to that differential equation, and we get du is equal to pi times dx. The only problem is we don't have a pi anywhere in the integral. If we had maybe something like this right here, if we had cosine of pi x and then a pi dx at the end, life is good. Makes things really easy for us. We could just take this entire thing in the box and replace it all with just du. But unfortunately, sometimes life throws you a curveball. We have to make some kind of a modification that can account for the fact that we don't have pi in the integral. Well, the good thing is pi, it's easy to handle. All we need to do is divide both sides of the differential equation by pi to make that go away, and we have only dx, which is exactly what we want. So this tells us that dx is equal to du over pi. So we're going to replace all of this with just du over pi. So I'm going to actually just erase all of this in the box and replace it with du over pi. Dx is equal to du over pi. So pi is a constant, and 1 over pi is certainly a constant as well. So one thing we can do is we can take this 1 over pi, we can move it out front and make things a little easier to deal with. So now all we need to do is do the substitution. So we already did the du part of the substitution. All we need to do now is the u part. So we know u is equal to everything in the parentheses. So this is cosine of u. All right, so things are pretty easy for us now. We know how to take the antiderivative of cosine. We know it will just be sine. So if the antiderivative of cosine of x is sine of x, the antiderivative of cosine of u is going to be sine of u. And it doesn't matter what function u is. You could be any function under the sun, and it would still have the same result. It would still be sine of u. But let's talk about why we don't have to have a plus c when we're doing a definite integral. So suppose we leave a plus c in there. And then we're going to take our antiderivative. We're going to evaluate it at our low endpoint. We're going to evaluate it at our high endpoint as well. So by this point, we're pretty good with the process. We're pretty good with our arithmetic, and we know how this is supposed to work. We're going to do sine of whatever our top endpoint is. We're going to plug this in for x. And then we're going to subtract the same exact thing that occurs when we plug in our bottom endpoint in for x. So in this case, we're going to be plugging in pi over 3 for our x value in this case. So they both have a plus c. What happens when we distribute, though, is we're going to have minus sine pi of x minus c. So that's why we don't have a c when we're doing a definite integral problem. The c's cancel each other out. We have a plus c, and we have a minus c when we distribute. So that's why we don't have to do the plus c. And we're kind of running out of time, but we may have time just to finish this real quick. And I'm sorry we didn't really have enough time to delve into the other integration topics, but I highly recommend you just go to my YouTube channel and review some of the videos. I think I have quite a few integral videos up there if you want to review anything at all from this class. And if you want me to make any more videos covering anything at all, just let me know, and I'd be happy to do that for you. So let's finish this real quick. We don't have the plus c. So the 1 over pi is not going to be affected by anything occurring on the inside of the brackets. This is going to be unchanged. So we're going to have sine of, well, actually, this is not going to work very nicely, because when we get down with it, we're going to have sine of pi times 5 pi over 6. It's going to turn into 5 pi squared over 6. And if I'd thought about this a little more carefully, I probably would have had a better function to use, because this is not on the unit circle. If we had just 5 pi over 6, it would be pretty simple to do. We know sine of 5 pi over 6 is just 1/2. But we don't have anything in terms of pi squared on the unit circle. So it was just a poor choice on my part, picking this to be the function. So that is all we have time for today. It's been a real pleasure teaching you guys. I'm proud of the progress you've all made. We've all learned quite a lot. And I hope you enjoy the rest of the year. Hope you have a really great 2021 and good things for the future for you guys.